Welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Stephanie Gill, who is an assistant professor in the John Paulson School of Engineering and Applied Sciences at Harvard University. So something about Stephanie, she holds a Bachelor of Science from Cornell and both a Master of Science and a PhD from MIT CSAIL, where, broadly speaking, she worked on multi-robot coordination and control and system identification and model learning. Then after her PhD, she held an assistant professorship at Arizona State University until 2020. She was for a while a visiting assistant professor here at Stanford, and then she joined Harvard. Her work, broadly speaking, centers around trust and coordination in multi-robot systems. And in this particular topic, she has won a number of awards that I listed in the bio, which is quite impressive. And also she recently had couple of patents awarded in this area of networks for multi-robot systems. Today's talk is about resilient coordination in networked multi-robot teams. This is very exciting work, and I'm looking forward to hearing more about it. Without further ado, Stephanie, go ahead. The stage is yours.
Thank you so much, Joelle, and thank you for everybody for attending the talk. So I'm excited to talk to you all today about the work that we're doing in resilient coordination for networked multi-robot teams and also decision-making in networked multi-robot teams. And so before getting started and telling you more about what we do, I'd like to give a little bit of motivation through an example to give an idea of the kinds of problems that we think of and what motivates that thinking. So looking back at the connected network, the first time that devices were connected over long distances and were able to communicate, pass data, and this was a very important part, was the internet. And this changed the world. This changed the world in the way that we communicate, in the way that services were available, etc. And then as we understood how to continue to be able to remain connected, it enabled this information exchange even as devices became mobile. This is the current phase of this evolution that we are in now, the mobile network. And so what we think about is the next phase of this evolution, where now, instead of information exchanged being available even as these devices move, the idea is that the mobility aspect is a primary aspect of the network, and this is the multi-robot network. And so these networks are characterized by a few things. One is controlled mobility, the fact that they can sense on board, that they have intelligence on board, and that they have, of course, the information exchange. And so the question now that we ask is, what will it look like? What will multi-robot networks enable in terms of services, in terms of changing economies and the world around us? And so our work in the lab looks a lot at this confluence of controlled mobility and information exchange, where the information is used to enable a lot of the enabling the decision-making, etc. And then the feedback loop is the decision-making. So how can the communication then further support our decision-making? So along the way, there are a lot of major challenges in terms of making these multi-robot networks really reach their full potential in society and in the world around us. And today I'm going to focus on two particular major challenges that we look at. One is on the resilience side. So the idea is, how do we achieve resilience coordination for these systems, even if some subset of the network might be not trustworthy, or might have some either malicious information or even malicious agents in the network. And the other is on long-term decision-making under uncertainty. So we want these robotic systems to actually be able to operate in the environment and continue to make decisions in the environment, even though the environment might be largely uncertain. And so I'll start with thinking about this resilience question. And so really to understand what it is that we look at there and what are the problems that we focus on. First, I want to talk a little bit about what security of cyber physical systems even means. So I'll start with a few examples that have really been coming to light through a lot of research that's been happening in terms of cyber physical systems and their security. So one example is in location spoofing, where researchers have been able to show that by spoofing and manipulating the GPS links, yachts could actually be driven off course. Another is hacking of connected vehicles. So out of the Senator's Office of Massachusetts, there was a technical report, in addition to a lot of research, that shows that connected and intelligent vehicles can actually be misled. For example, you can have imitation attacks where some of the sensor readings can be manipulated and rewritten and taking over control of parts of the vehicle. Also, Sybil attacks. So Sybil attacks are particularly detrimental, and that's where an agent can actually spoof other entities in the system in order to gain a disproportionate influence on the network. So for example, here, some of the research has showed that a Sybil attack on crowdsourced mapping applications could actually make certain road segments look congested by emulating many false IDs in a particular part of the network. So the important takeaway here is that with cyber physical systems, and multi-robot networks is an example of a cyber physical system, the behavior really plays a critical role. And so it's not only about authentication and the ability to access the network, but it's also what do you do, or what does an agent do once it is on the network? So the behavior now is very important, and that means that we also need performance guarantees. So now, in terms of resilience of a multi-robot system, I'm going to use a few terms throughout the talk. So here, the degree to which success can be achieved for some coordinated objectives. So most of the time, multi-robot systems have a coordinated global objective, and the degree to which they can achieve that coordination is what I'll call the performance of the system. And the degree to which that performance can be maintained in the face of an attack is what I'm going to refer to as the resilience of that system. And so we must characterize and mitigate the impact of untrustworthy agents on performance. And so that's what we do, and that's what I'll talk a lot about in today's talk. So to give an example of this, let's take the example of consensus. So here are some smart and connected vehicles, and the true potential of how they can change, say, services, maybe transportation services, is achieved through coordination. So for example, a lot of research has been done on using coordination to be able to negotiate intersections and traffic management in that way. So what happens if there's an attack on consensus? So here we have agents or cars in this example that are trying to reach consensus on a heading direction. And if there's an attack on that consensus such that they can no longer agree, then on the left is what such an attack might look like in a schematic form. On the right is what such an attack might look like in a graphical form. So here is the true average, or the true heading that all legitimate agents in black would like to be able to converge to and agree on. And then here on the right, these red arrows is the heading direction that's injected by a malicious agent, say. And so if you have no way to understand that such an attack, in this case, a Sybil attack, is happening, then all of the legitimate agents might converge to the input of the malicious agents, or they might not converge at all, in which case you'll get divergence. And so we wish to quantify performance. So can the system reach convergence or not? And we wish to bound the deviation under the attack. And ideally, we want to also learn or mitigate the effect of the attack over time. So a classical result in consensus says that agreement can be attained if there are certain limits on the number of malicious agents in the network. And this result has been pretty important for understanding consensus under adversarial influence, and much work has built upon this and has really pushed the envelope in terms of our understanding of how to reach agreement when you have adversaries. And so what I'll do is I'll talk about approaches to security, and I'm going to bucket these into two kind of major areas. One is data-based, which is similar to what I mentioned in the previous slide, where the idea is to detect anomalies and characterize adversarial influence by using the data that is being transmitted between agents in the network. Now, this is helpful, and it definitely can make our systems more resilient. However, this can quickly lead to practical limitations. For example, that less than a half of the network connectivity can be malicious, as mentioned in the previous classical result. So another body of work on the other side tries to look at physicality-based security approaches, where the idea is to not just use the data that's being transmitted between agents, but also something about the physicality of the system in order to understand when security risks exist. So what exactly does this mean? Well, here's the idea. The idea is that if you have multiple agents, like cyber physical agents or robots in this example, that are in an environment and they're operating in an environment, they have many additional avenues of information at their disposal. One is that they have onboard sensors, so they can sense each other, they can sense the environment, and they also have communication or information exchange where they can share these observations with each other. So the idea is, can we use this physicality to help us additionally secure these systems? And I can just summarize this by saying that as these embodied agents physically interact with the environment, they can learn about the environment and also about each other. And that's kind of the primary idea that we want to build upon. And so then there's been a lot of work that's been specifically looking at exploiting the physicality of cyber physical systems for the purposes of resilience. For example, location validation. So how can I cross-validate location information through GPS signals, through data sharing, watermarking, where specific private signals are injected into a transmitted signal in order to be able to detect, for example, any kind of manipulation to particular sensors and actuators. Residual analysis using observers, so understanding deviation from behavior. Wireless signal processing, so using the actual signals themselves to try to understand qualities of the transmitting agent. And behavioral observation. So these are more reputation-based metrics of trust. So currently, there exists a very exciting opportunity to think about how that physicality can really change the way that we think of resilience in multi-agent systems. And so this is what I call physicality-based trust. And the upshot is that this can lead to much stronger resilience guarantees than just using the data. And this is, we just recently wrote a survey article on this idea that's been submitted and hopefully will be out soon. So there are different types of trust that can allow us to achieve new performance guarantees in terms of resilience. One is reputation-based trust, where we essentially have a history of observations and we compare against some nominal behavior model. There are network measures of robustness, so ways to understand the redundancy that is allowed through the network due to its connectivity. And there's stochastic trust, where we can quantify the likelihood of a link in the network being untrustworthy. And so I'm going to focus for a while on this last type of trust, which is stochastic trust, and give an idea of what we can do with this type of trust. So here's the idea more specifically. So assume that I have some observation of trust. I'm going to call it alpha ij, so that for every agent I, let's say I is a legitimate agent, and j, which is one of its neighbors, the alpha ij is a random variable that takes a value in the interval between 0 and 1 and represents the likelihood that agent j is actually a trustworthy neighbor of agent I. So if here's my network, we assume that now all agents are still transmitting a value. So this is their data, some value x. But now we also get this alpha ij, which is a stochastic value of trust. And the important and mildest assumption that we can have on this alpha is that in expectation, this alpha value will look different if it's coming from a legitimate agent versus a malicious agent. And in particular, this epsilon here captures how certain the observations are. So in essence, it's how different in expectation these alpha values will look when they're coming from a legitimate agent versus a malicious agent. So where do we get such alpha values? There are many different places where you can imagine measuring such alpha values. And I want to give one specific example, which is using the wireless, the actual wireless signal itself that's used to transmit the data. So assume here that you have a malicious agent and it spoofs a cluster of other agents in the network. So this is the Sybil attack that I talked about previously. Now, if you look at the actual signals that are transmitted between the agents, you can qualitatively understand that they will look much more unique if they're coming from physically different agents versus if they're coming from physically the same agent. So the intuition is that if I could take these wireless signal fingerprints from the transmission, and I can quantify the similarity of these profiles or these fingerprints, then that could be one option for the alpha ij values, the stochastic values of trust. And importantly, this is not just an intuition, but it's actually something that we can formalize, where we can actually compute alpha values for wireless signal fingerprints with the particular property on the bounds in their expectation, depending on if they're coming from a Sybil agent or a legitimate agent, who in this case is not a Sybil agent. And this is what it looks like in practice. So if I take a histogram of many alpha values, this is my server that I'm trying to control. These are some spoofed agents in the networks. These are legitimate agents in the network. And if I look at the alpha values that are coming from each of these transmissions, if they're coming from the spoofed agents, you will see them as red here. So this is their actual empirical distribution. Similarly, for legitimate agents, the green shows their empirical distribution. And you see that indeed they are concentrated around these expectations. And so then we have this property holding, which is the one that we were hoping to see for malicious agents. Okay, so now the important thing is to say that this is a general idea. So the wireless signal fingerprints provide a concrete example of trust observations, but this is a more general concept. And so from here on, I'm going to use this idea as an abstraction. And I'm going to focus on the bigger picture, which are questions around how to use values of trust in control and in decision making. And so in order to do that, we need a mathematical framework for utilizing trust. And so we developed a mathematical framework for utilizing trust to make coordination more resilient. And we ask questions of this form. Can we learn who we can trust in the network? How does this information of trust propagate through the network? And in particular, how does the topology impact this? And then what does this mean for the performance guarantees of our multi-agent coordination? Okay, so going back to the consensus problem, I want to talk about how we might be able to use these stochastic values of trust in consensus. So here we assume that each agent has the data that they're transmitting, so this value x at time t. And here is the graph, so of the actual agents that are trying to coordinate in this case. And every agent is just going to run a average consensus protocol where it takes the weighted sum of its average of its agents' opinions and computes the average and updates its value in the following way. And these weights here, importantly, dictate the influence that any neighbor J will have on any robot I's updated value. And so now I'm going to look at that network. I'm going to abstract it where blue nodes mean legitimate agents, red nodes mean malicious agents. And we don't know who is malicious and who is legitimate. But for the purposes of understanding what's happening, I'm going to write the dynamic in the following way, where I'm going to separate the influence of the legitimate agent values and the malicious agent values. And I'm going to assume that I don't know how malicious agents are updating their values. But for the legitimate agents, we do know that they're going to use the standard protocol. Okay, so here's the consensus dynamics, and then the legitimate agents now are the agents that follow the consensus protocol when they update their value X, and malicious agents are agents that do not, or that are not legitimate. That's how I'm going to define them in this case. And we assume that the subset of malicious agents is unknown a priori. Okay, so what does this look like? In the flocking scenario, on the left-hand side, if we have no way of understanding who is legitimate and who is not, then what you will see is if this is the consensus values on the y-axis, we have the consensus values of all the agents. In red, I have the spoofed agent value or the Sybil agent value here. Then what you will find is that over time, all the legitimate agents will converge to the value of the malicious agent, far and arbitrarily far, in fact, from the true average that they're trying to agree on. What we would like is something more like what's on the right-hand side here, where even in the presence of an attack, we can still arrive at a consensus that is closer to the true average. Even though we might not know with certainty who is malicious and who is not. Okay, and then the deviation from where we're trying to converge, the true average, I'm going to call that phi of m. And ideally, we want to make that phi of m small and at least bounded if we can. And this is the subject of the first paper that I'll talk about here, which is about characterizing trust and resilience for distributed consensus. So in this problem, what we want to do is we want to find a new definition of the weight matrix and some observation window, time t0, such that we have the following bounds on our deviation here, where if this is the legitimate node's value over time, and this is where I'm trying to converge, which is the true average, then I can bound that error within some delta, my deviation, within some given probability of error. And so just for understanding graphically what's happening here, this is the deviation that I would like to characterize and bound, if possible, by some delta max. So now I want to re-examine that protocol of my consensus and take into account these stochastic observations of trust. And now I want to define my weight value as a function of those alphas of those stochastic observations of trust. And I'm going to make a few assumptions. One is that the graph is sufficiently connected, which means that if I remove the malicious agents, I still have a way for information to flow through the network. So my legitimate agents are connected even as I remove malicious agents. And I'm going to assume that these alpha values are independent over time and that the values are distinguishable in the attack or no attack case, which goes back to bounds on the expectation in the two cases. And I'm also going to assume that the agents can observe the network for some time t0 before I start running the consensus. And in the analysis, we're interested in understanding the influence of that observation window on the, for example, deviation from nominal behavior. Importantly, we continue to run consensus even after time 0. And we seek stronger performance guarantees than what we can get when these stochastic observations of trust are not available. And in particular, we really want to be able to quantify what that stronger resilience is. Okay, so now let's go back to how to define these new weights, which I'm going to call resilience weights. So first, we take an observation history, a running sum of all of the alpha values that each agent receives over a particular link, say ij. And I'm going to take this over time. Graphically, what this might look like is the following. If agent I is talking to agent J and J is actually legitimate, over time, these alpha values will look, or this beta, sorry, the beta will look something like this. The alpha values themselves are noisy. So we might sometimes be above 0, which means that that's a trustworthy transmission, or below 0, which means that that's likely not to be a trustworthy transmission. But over time, because of the expectation, we expect that this is going to get more and more positive. Similarly, for the malicious agent case, we might have some misclassifications in the beginning, but over time, we expect that this beta is going to become more and more negative if J is actually malicious. And so we use this intuition to derive a way of choosing our trusted neighborhoods. So I'm going to choose, or agent I is going to choose its neighborhood such that it includes agents with some positive beta value in its neighborhood, and it excludes agents that don't have a positive beta value. And that leads to a new weights definition, which I'm going to graph here in this blue axis, where the weights are essentially going to, so I'm going to take this example here, are going to be 0 for the case where an agent is not trusted at time t, and it's going to be some non-zero value that's 1 over the number of trusted agents in my neighborhood whenever it's positive. And I'm going to keep doing that over time so that as I get more and more observations, more and more alpha observations, I want to be able to converge to something like a nominal weight, what I would expect if my neighborhood is actually the neighborhood of trusted, legitimate agents. Okay, so what does that mean then for the consensus dynamics? In order to really understand what's happening with the consensus dynamics, I have here the consensus dynamics that is written for, it's broken down into 2 pieces. The first piece is the contribution of other legitimate agent values to my legitimate agent values. And then the second piece here is the contribution of malicious agent values to my legitimate agent value update. And so I'm interested in these 2 dynamics to understand how this new weighting is going to affect my updates over time. And so the approach then about how to see, or about how these resilient weights can now lead to a more resilient consensus algorithm is the following. First, I want to be able to show that the probability of misclassification, so the probability of an error, decreases exponentially with time. And then I want to be able to show that both of these terms converge to a finite limit almost shortly. So we have convergence, in other words. And then further, I want to bound the influence of the malicious agents in the case of errors in the following way. So I want to be able to bound the total amount of error that an agent or malicious agents can contribute to the network if I use these resilient weightings. And of course, that error comes from 2 directions. One is misclassification of malicious agents as legitimate, and then misclassification of legitimate agents as malicious as well. And then I also care about the influence of the observation window T0. So how many observations I'm able to collect before making this determination. So in this graphic, this choice of T0 would be great because at this point, I've had enough observations that now my beta is much less likely to cause misclassification errors. Okay, so the first result that we have along these lines is saying that actually the misclassification probability, both misclassification of J as malicious or legitimate, depending on the truth of J's identity, is going to decay exponentially in the number of observations. And a corollary to this is that the number of failures occurs finitely often in the limit, which implies that the influence of malicious agents can, in fact, be bounded. And so that's important because that leads to this important result, which says that even with malicious agents in the network, if I use resilient weighting, I can now converge to some agreement between all of the legitimate agents. And this is true independently of the number of malicious agents in the network. So this is different from the classical results in Byzantine consensus. And then further, we can also characterize the maximum deviation, delta max, and we can characterize this specifically as a function of the time, the amount of observations that I'm allowed to collect. And so we do have particular closed form results for these terms here that bound this deviation, which I won't put here because they're a little bit messy algebraically, but they are in our related paper. Okay, so what does this mean numerically? What this means is that with resilience weights now, we are able to achieve behavior that looks something like this, where our deviation from the true average is actually bounded by some deviation delta max. And in simulation, this is what it would look like. So if this is the true average, these are my legitimate agent heading values. They're able to converge to a value much closer to the true average, even when there's malicious agents that are inputting the wrong values. Okay, so now I also want to just point out the role of T0 here. So remember, T0 is the amount of observations that I'm allowed to collect before running consensus, but I continue to run consensus even afterwards. So the observation time here has an impact on the amount of deviation that I end up with. And so this is just pointing out what that looks like. So this is the malicious agent input. If T0 is 0, means that I do not collect any observations before starting consensus, then you get a pretty large deviation. But as that T0 gets larger, even for small values of T0, I'm able to manage the deviation. I'm able to achieve much smaller deviations, in fact, arbitrarily small, as the T0 gets larger due to that exponential decay in the error, in the misclassification error. Okay, so that then tells us how we might be able to start using this additional information of trust, these stochastic observations of trust, for being able to say something stronger in terms of our performance guarantees, even as the number of malicious agents gets larger in our network, which shows promise for being able to put these systems out into the real world where you can't necessarily manage how many malicious agents are going to end up in your network. However, there's a need for learning trust over different network topologies. So the previous example talked about undirected graphs. Here in the case of directed graphs, we have a malicious agent, and through the theory that I just mentioned, we can learn, so outgoing neighbors of this malicious agent can learn that it's malicious. However, the other agents that are upstream of the malicious agents in this case cannot learn its true identity because of the directionality. And so then what you would end up with is a convergence plot that looks like this. You still achieve agreement, but here's the true average and you're under the true average. And interestingly, if this is the malicious agent value, this is not even in the convex hull between the malicious agent values and the true value. And the reason is because you actually have something called leakage. So here, it's not that the malicious agents are contributing malicious values to the consensus, but you're actually losing information because these agents cannot properly adjust their weighting because they cannot learn that this malicious agent is actually malicious. And this is also a difficulty for many different coordination tasks, including, of course, average consensus, but also distributed function computation, estimation, distributed optimization tasks. So many of these tasks, the topology plays a major role, and whether it's directed or undirected will be important. So in particular, learning these out neighbors and the true legitimacy of out neighbors is also important and needed to achieve many particular properties, such as balanced graphs, doubly stochastic weight matrices, etc. So how can we do this? How can we learn trust over directed graphs or over different topologies? So the problem here is that asymmetric information in the network arises from the directionality of the graph. So if agent I wants to learn about agent Q, but does not have direct trust observations for that agent Q, we want to be able to derive something called an opinion, which is maybe not a direct observation, but is available for any other agent in the network, even if it's upstream or downstream. And we want those opinions to converge almost surely to the true trust values for any agent, say Q in this case. However, malicious agents can also be anywhere in the network, and they can send arbitrary opinions in the range of 0, 1. And so the challenge becomes understanding how to manage these different information flows, some being trusted, some being not trusted. So the difficulty that arises from directed graphs is that there can be one or more malicious agents between any agent I and agent Q, which leads to heterogeneous information flows. However, we still have the connected assumption from before, where we assume that there does exist at least one trusted path in the network overall that connects legitimate agents to one another, even as we remove malicious agents. But then the key becomes, how do we know and how do we learn which are these trusted paths of information? Because obviously we don't know where the malicious agents are or who they are. So what we do is we design a new learning protocol that updates the trusted neighborhood in a very similar way to before, but now we have this additional parameter here, which are the opinions. And the opinions are set to 1 if I have a direct observation of a particular agent, Q, and it's trustworthy. I set it to 0 if I have a direct observation and it is not trustworthy, or my beta value is less than 0, similar to the previous undirected case. But now the opinion, I'm just going to set it to be the average of my opinion that I get from other 8 neighbors in the case that I do not have a direct observation of some value Q. So now what that looks like is I'm just going to jump to the actual result that we're able to show, and this builds upon the result for the undirected case. So for the undirected case, we know that directly observing agents will eventually converge to the true trust value for legitimate agents. Now what we say in this work is that any indirectly observing agent will also converge to the same opinion directly. Will also converge to the same opinion as directly observing legitimate agents almost shortly. And I'll just give a quick idea of how this works or why this works. So if I look at the opinion dynamics, so here's the weight matrix, and I break it down into 3 elements now, which come from the directivity. One is that I have the agents or the weights of the agents that are indirectly observing some agent in question, Q. And I have the weights of the directly observing agents for Q, and I have the weights of the malicious agents. And of course, this is just for the analysis. This is not, we don't know what this is. So this is just kind of breaking it down to really understand what's happening. What we do know is that the weight of indirectly observing agents is a substochastic matrix. And recent results by Azimzadeh in 2019 allow us to arrive at the convergence that we need, which is to say that so long as there exists a trusted path in the network, which we know it does because of the sufficient connectivity assumption, we can use this to actually show that even this matrix here is convergent. In other words, the information from legitimate agent paths will dominate over time as we get more and more observations of malicious agents in the network. And this leads to our convergence result. And then here are just a few quick numerical studies to show that in low connectivity networks, we are able to converge. And also in high connectivity networks, we're able to converge, but probably faster in this case. This paper doesn't necessarily look at the convergence rate, but we can see from simulations that, as expected in high connectivity networks, we converge more quickly. So what about other topologies? What about dynamic topologies, where now my agents are actually moving between different areas or different sites in the environment, and they have intermittent communication or intermittent observations of each other? We also look at this problem in our work, and we understand what happens to the learning of trust over time, and how might we control agents to be able to acquire more observations of each other if they need to establish trust. So overall, I will just mention that our resilience in multi-robot coordination, we've looked at many different problems. So I've just talked a lot about the consensus problems, and that we're able to still achieve convergence or agreement, even in the case where more than half of the network connectivity is malicious, because we use this additional information through the stochastic observations of trust. We've also done work in resilient distributed optimization problems, where the idea is that we have malicious agents that are contributing potentially malicious information. However, we also have stochastic observations of trust, and under this, we're able to show convergence, and we're able to also show some results on convergence rate for this case. And then also in the theme of resilient hypothesis testing, so in distributed event detection, we've also looked at the effect of malicious agents here. So the same idea is applied across, where by using stochastic trust observations for weighting, we're able to arrive at provable resilience. And so just to give you an idea of what this looks like in practice, so both the theory and the practice, here we have a traffic estimation problem, where the idea is that agents are trying to estimate, as they move through the environment, whether a particular segment of the road is congested or not. And so here, this is similar to, say, like a Waze application or a Google Maps application, where you have multiple agents, and they're all sending their observations of the traffic to a fusion center. However, in our case, we're interested in the part where many of these agents might actually be malicious and might be sending the incorrect information to the fusion center. And so similarly to before, all of these agents are traversing a segment, and they're reporting back a value. So here's the data that they're reporting, and we have an alpha value that is being sensed by the fusion center. And then here we have a Sybil attack. So many of these agents are actual Sybil entities. So they're making a traffic segment look congested when it's not. And the legitimate agents are just reporting their actual sensed value to the fusion center. And importantly, here we have, so here are the Sybil entities. The fusion center is collecting these wireless signals and is processing this as fingerprints to try to understand who is trusted and who is not. And then this is just showing qualitatively that the profiles, the wireless profiles, will look similar for agents that are actually Sybil entities. And then in addition, this is what it looks like. So this is the actual histogram of the alpha values. You see that they're concentrated around 1 for the legitimate case and around 0 for the malicious case. And then the reported values themselves also are subject to error, because we assume that the sensors, even on legitimate agents, do have some error. And so the robots will report a 0 in the case that they think the road segment is not congested, and it will report a 1 in the case that it thinks that the segment is congested. And they report these values back to the fusion center, which then makes a decision as to whether the road segment is actually congested or not. So the decision of the fusion center is what you see here in the upper right corner. The oblivious fusion center just takes all of the values that are reported and makes a decision. Here's ground truth on this map. So you'll see that oftentimes the oblivious fusion center just it does not agree with the ground truth because it is under a Sybil attack and doesn't realize that that's happening. Whereas our two algorithms here that do use these stochastic observations of trust are able to understand the true state of the environment a lot more often. And so here you see this is the average error. Our two approaches are in magenta and yellow here. And this is the oblivious fusion center. So you see that we're able to drive down the error by using these additional stochastic observations of trust in an event detection scenario. So I talked about a few different types of trust. In the first part of my talk, I focused on stochastic trust, and now I want to talk just for a few minutes about network measures of robustness. In other words, how we can use the level of connectivity of the network. And so this was work that we recently published in TRO, actually, also at RSS previously. And so the idea here, just again bringing together the theory and the experiments and the practical aspects. So what we would like is that as agents are navigating through the environment, they need to be able to navigate and agree at the same time. So here's the consensus problem again. And we want them to maintain a resilient formation as they're moving, and they have a particular communication range to each other. So the problem is that they're trying to achieve flocking. So they're trying to agree on a heading direction as they're moving through the environment. And there's one adversarial agent right here that over time, if it picks a particular point that the network is vulnerable, has a weak connectivity, it could inject an attack where it changes the heading direction, thereby causing the network to split. In other words, not to achieve agreement on their heading direction. And so what we would like to do is understand how to prevent this from happening by using the connectivity as a constraint in their control. And so here we're looking at the collisions that could happen through the environment, but also now this resilient topology, network topology. And what we find is that the environment can often force a trade-off between resilience and navigation. And we must characterize when this happens and determine how to handle it. And so we look at, in terms of this problem, we look at resilience as a hard constraint where we can satisfy it, resilience as a soft constraint, so understanding when we absolutely cannot satisfy resilience, resilient topologies. And we also target agreement between theory and practice. So as these agents move through the environment, how we can really understand how to kind of trade off between these two. And so one result that we look at in this context is what is the maximum size of an obstacle such that your agents here, shown as this formation, can navigate around it without reaching a critical value of resilience where it becomes vulnerable to attacks, for example, on consensus. And we looked at cases where resilience has to be treated as a soft constraint. For example, a narrow corridor, where if you really impose resilience is maintained, that the agents cannot successfully navigate. And then understanding how to put it all together, what you have here is the example now where we are using the local control barrier function that we derived that takes into account resilience and navigation. Here's the adversary. The adversary stages an attack, but even in the case of the attack, the agent in this case is not able to successfully break the network. So you see here the agent is inputting the wrong heading direction, but the other agents are able to maintain a connected network, sufficiently connected network, even as they navigate through the environment and around obstacles and avoid getting attacked successfully by the agent. So just to summarize this concept of physicality-based trust, using information extracted from wireless communication channels is one example of physicality-based trust, and it shows the potential of being able to use physicality to improve resilience. However, overall, this idea of deriving physicality-based observations of trust is still underexplored. And this is something that we're exploring in some of our new work, including this survey paper. And then I'll take maybe just the last couple of minutes here to talk a little bit about this piece of our work, which is long-term decision-making under uncertainty. So trustworthy coordination assists decision-making whenever a subset of the network's legitimacy is unknown. And this is what we've been talking about for most of today. However, we are also interested in decision-making when other elements are unknown. For example, the future state of the environment. And so in this example, for example, here we have autonomous pickup and routing, where you have multiple drones or autonomous vehicles that are routing through an environment, and they're trying to service requests. These requests can be pickup requests, they could be delivery requests, etc. Here we focus on problems of large maps, also large teams. So as the number of agents increases, how do you coordinate their actions without having your search space really blow up? And then unknown and variable demand. For example, the fact that these demands for pickup and deliveries change over time and can change drastically, for example, due to surges whenever something happens in the city, like events. And overall, we use a look-ahead based RL framework that looks something like this, where the first part here is we're actually trying to expand out the decision making over some small number of steps into the future, maybe even just one. However, this becomes very expensive in the number of agents and in the number of actions. And then we have some estimation here that's happening that allows us to estimate the future cost. And this is also expensive in the number of possible futures. And then at the end, we want to be able to learn some policy for all of the agents that we control in the network, and including all of the uncertainty that can come into play in the framework. And so we've looked at this problem in many different contexts. For example, in the case of pickups and drop-offs through a city, where the big problems here are the large state space and control space due to the multi-agent aspects, also the changes in the future demand. And most recently, we're also looking at this problem in the context of observation of whales in essentially natural habitats, where the problem here is that the agents you're trying to visit are only partially observable. So they have partially observable state due to the fact that we don't have constant sensor inputs of where they are located. And so this is some work that we've recently published. We'll be presenting at ICRA and also AMAS this year. So I'll end here. I'll just say that we use controlled mobility and information exchange very interchangeably in a control feedback loop, and that is really characteristic of a lot of the work that we do, and that this really leads to new results in terms of resilience and more capable coordination in multi-robot systems. I, of course, will thank my students, my collaborators, and our funding agencies that make this work possible. And then I'll leave you with a few final thoughts here, where the idea is that cyber-physical systems bring novel opportunities for both data validation and also establishing inter-agent trust. And that if we can really understand this and quantify this, then this really opens the door to a lot of new resilience tools that we will need as we start to take these systems out into the real world. Thank you so much. And with that, I'm happy to take questions.
Thank you very much, Stephanie, for the great talk. Let's open the stage for questions. You can either type the question in the chat and I will read it for you, or directly ask. I have some, so I'll start as an icebreaker. So sure. Very exciting work. It's very nice to see that you work on these topics of trust and resilience all the way from the single platform to a handful of agents and now even networks and mobility. It's great. A question that comes naturally is, how do you envision combining the notions of resilience at all different scales together, right? So here somehow you are presenting works where you consider the resilience of the net at the network level, the resilience at the platform level. but in thinking about a system that has all of these levels active at the same time, how do you think about enforcing resilience simultaneously at different scales?
Yeah, that's a really great question. So I think what we've done is we've kind of approached this problem from both sides. One is really trying to understand even the foundational mathematical tools that we have at our disposal. What can we say about using trust to be able to make decisions and fortify the coordination? Then when we start to scale up the problem, as you mentioned, Joelle, as we start to scale up the problem, then it becomes more challenging, even just from the point of view of scale. How to make decisions at this scale with this number of agents and over longer horizons. Now, bringing these two pieces together, how to use trust in long-term decision-making with large numbers of agents, this is something that we're looking at just now. So it's a pretty timely question.
Okay, great. I'm super interested into how these things develop. It's very cool. There is another question in the chat. Before I ask the other ones I have, Subrata is asking, is there any regulation concerning the multi-robots controlled mobility? I'm not sure I understand exactly what this means, but Subrata, feel free to complement the question if you can specify more.
Yeah, it's a great talk, Professor. But I'm interested to know with this, the important work on the trust, consensus, and very well. We understand there could be a malicious thing or a malicious regime on which your research is based upon. So is there any regulation? Because suppose I believe that you're working in the US system. So it is getting into a fruition, but is there any regulation from the state government or federal agencies thinking about the futuristic aspect of your work?
That's a really interesting question. So the answer is, I guess as of right now, we've been focusing mostly on the basic research questions. So even how to understand mathematically, can we use this to have stronger performance guarantees? I think the next step is understanding how to scale up, how to transition to government, etc. So we haven't so much been thinking about regulatory questions yet. But you raise a good point, and it's definitely something that we'll be working with industry and working with government in the near future to understand.
Yes, quickly, another one, just a connected one, because the next level is the drone part. And after that, it comes to the air taxi part. But the air taxi part is already piloted by someone. But the drone part is not piloted. It is falls into the regime of your research work. So I can understand that, Professor. Thank you very much.
Yes, thank you.
Thank you, Subrata, for the great question. So another question I had was, it was a very interesting that you presented this idea of leakage, this loss of information that you observed in experiments. Subsequently, you presented some ways to design policies and consensus to kind of mitigate for that. I was wondering if you also are thinking about the other side of things, where you can design a network in the first place to minimize these effects. So instead of the policies, the operations, I would say the network design.
Definitely. So that was so I mentioned 3 different types of trust, and one of them was regarding the topology itself. And so in the control barrier function work, that was the objective that we had in mind there, that you want to maintain the network with a certain level of redundancy in order to be able to reduce the ability of a malicious agent to actually have any impact. So there are definitely challenges, and one of the challenges that we look at in that work is how do you maintain that type of redundancy and resilience in the topology, even as the agents are dynamic in the environment. The environment is changing, the agents are moving. So this is a very challenging problem. And in fact, there's some configurations of the environment that just preclude your ability to maintain that resilience. And so part of that work is really trying to understand what those situations are and input this into a global path planner as a constraint even, so that a global path planner might be able to plan paths in advance, understanding where these deadlocks will come in, where the resilience will essentially meet the constraints of the environment, and how to maybe navigate around those deadlocks. So that's the idea there, although I should say that it's not always possible. Some environments, like for example, small constrained spaces, make it very difficult to be able to maintain that topology.
I see. That's very interesting. Thank you. Actually, I have a final question related to, I was actually not aware you started working on mobility as well, and it's very interesting. So is there the problem in the example you provided with drones or pickup deliveries? Is there what you're trying to solve, some sort of more reactive rebalancing strategies for your fleets to black swan events or kind of unexpected events? Is that the idea?
Yeah, that's a really great question. Yeah, so the idea there is to try to, you want to do two things. One is you want to try to predict as best as possible what could happen in the future, and you want to be able to kind of proactively position agents such that they can absorb some of that change in the environment as much as possible. And so we are. So one of our paper that we are going to submit, or that we are going to present at AMAS this year, is called surge routing. And so the idea there is to scrape the internet for information from events that are happening and reviews on those events to try to understand how popular is an event and how likely is this to create a surge. And if it's likely to create a surge in demand, our policy will essentially learn to kind of position agents in such a way that they can absorb that new swing in events. And so we are looking at ways to try to understand and control for that. And then the second piece on the rebalancing is the stability aspects. Can we ensure that we have enough agents in a particular region of the map at any time such that your learned policy can provably maintain stability? And so that's the subject of our ICRA paper that we are presenting also this year. So this is all kind of some of our newest work that we're putting out there. Similarly, on the resilience side, we also have very kind of recent work, but yeah, so we're looking at that.
Very cool. So this ends in the reading list right after this talk. So is there any other question for Stephanie? I don't see anybody raising their hands. So I think you left your email in case people want, oh yeah, it's on the slide. If people want to reach out. Thank you again very much for taking the time. It was great to get to see some of this work. And also good luck for the next steps. I look forward to meeting you in Boston.
Thank you so much, Joel. Likewise.
And thank you everybody for joining, and see you all next week for the next Autonomy Talk. Bye-bye.
Bye-bye.